So welcome back, everybody. Dr. Johnson here for our lab on projectile motion. So we've been talking about motion in one dimension, one direction. So just going in a straight line, going backwards, speeding up, slowing down, and that was fun. But now we're going to start talking about motion in two directions, which is twice as much fun. So it's exciting because there's lots and lots of applications. I like sports applications. So like you're lining up the free throw, or your team's down by 5, last second Hail Mary. These are really good examples of projectile motion. Pop fly, chipping up on the 18th green with your pitching wedge. Really good examples of projectile motion. Projectile motion is when you have an object moving through the air and the force acting on it is gravity. We're ignoring some of the other forces like air resistance and things like that. So quickly, I want to do a review from some of the stuff we've talked about before, some of the terminology, I suppose. We talked about distance and displacement, and you learned in your lecture about vectors and scalars. Distance is how far you've gone. It's a scalar quantity, so it's just how far you've gone. If I've gone around a track is 400 meters, so my distance is 400 meters. Your displacement is a vector quantity, so it has to have direction. It's a straight line distance from your starting spot to your ending spot. So if I go one time around that 400 meter track, I end up back where I started. My distance is 400 meters, but my displacement is 0 because I ended up back where I started. Speed and velocity are two other terms we've been talking about. And again, it's a vector versus a scalar. Speed is a scalar. It's how fast I'm going at a given time. The velocity is how fast I'm going and what direction I'm going in. It's a vector quantity, so it has both the magnitude, the amount, and the direction that it's going in. And acceleration is how your velocity is changing. Those are things we've been talking about quite a bit over the last 2 weeks. The study of this type of motion is called kinematics. It's part of mechanics inside of physics. So that's sort of the map of things where we're at. We've been talking about graphing. We talked about position versus time graphs that tell us where you're at any given time. So I can look up where I started, I can look up where I ended, I can just use the graph to find out where I'm at any time. I can also look at how the graph is changing. I can see how my position is changing with time with the slope of that graph and find out my velocity at any given moment as well. We've also worked with velocity versus time graphs, where you can just look on the graph and read your velocity at the beginning, your velocity at the end, or at any time in the middle. You just look on the graph and read what your velocity is. Similar to the position time graph, I can use the slope to find out how my velocity is changing with time, and that's called your acceleration. So the slope of a velocity time graph is your acceleration. And a third bonus thing you can get out of a velocity versus time graph, if you take the area underneath the curve, you can find out your displacement. So you get 3 things out of that graph. That's pretty awesome, right? That's 2 weeks worth of physics packed into like a minute and a half. If you need to watch it again, then great. There's some equations you've talked about in your lecture. We've alluded to them in lab, but they are actually in your lab, right on the first page of the lab. They're kinematic equations, and they're pretty neat. There's 4 of them because there's 4 different variables, and you can solve for missing variables. It's they're really handy. I'm sure you're talking a lot about them in lecture. I did want to show you something kind of neat for my calculus-minded people. So if you're not calculus-minded, that's okay. You can still know it. Knowing stuff is fun. So the equation we have for your position, so change in position or displacement is going to equal your initial velocity times the time. Just making sure I get my notation right, because I want to be consistent. Every book I use uses a different notation. Plus 1/2 the acceleration times the time squared. The equation we have for velocity, the final equals the initial plus a times t. Now, this is kind of neat. I don't know, I'm a nerd. I like this kind of stuff. But what happens if I take the derivative of that equation? If you've ever taken a calculus class, you know what a derivative means. It's how this thing is changing. I'm going to take the time derivative. So how is this thing changing with time? And it's not a hard derivative, but if you've never taken calculus, you wouldn't know how to do it. But if you have taken calculus, you know the derivative of this first term is v initial. And the derivative of the second term is 2 times this stuff. So the 1/2 cancels out, and we end up with a times t. So the derivative of that first equation is that second equation. What does that mean? That means that velocity is the change in my position divided by time. So pretty neat. Not only is it supported by the physics that we've done so far, but math also says we're doing it right. So way to go. So we're going to talk a little bit about projectile motion now. That's just review. That's stuff we've been talking about before. We talked about motion in one dimension, and we said a ball rolling across the table, it's moving. We could graph its motion. We can see how it's going. If it's falling, if a ball is falling, we did some graphs last week with the match the graph where we were throwing one up in the air and having it come back down. That's still one dimension, right? Just up and down. This one's just left and right. What happens when it's happening at the same time? What happens when it's both going up and down and also left and right? Like this. It's going up and coming back down, but it's also covering distance from left to right. That's projectile motion. That's two-dimensional motion. The really cool thing here is that the motion that's happening up and down and the motion that's happening side to side, they happen at the exact same time, but they happen independent of each other. So I can look at the motion up and down and the motion side to side, I can look at it separately. So let's take an example. Let's say I roll this ball, it gets to the edge of the desk and it flies off the edge. So we have our ball is rolling, and every second, or every time increment, doesn't have to be a full second, but any increment of time I take, as long as those increments of time are the same, it's going to move the same distance because it's moving at a constant velocity. You remember the first week's lab? That's kind of what was happening there. So the distance that's gone here is the distance that's gone here is the distance that's gone there. And if the table continued, if it just was more table instead of a cliff here, it would do the same thing. Same distance. Same distance. Same distance. So this is the same as this, is the same as this. It's not exactly drawn to scale, but pretty darn close. Always the same. If I have a ball that I just drop, if I just have it here, and I just drop it, well, that's not going to be a constant velocity, and I'm sure we've talked about that before. It's going to start off going kind of slow, so the distance it travels, because its initial velocity is 0, and then it starts speeding up when I let it go, and it's only going to travel a little bit here. And then the next one is going to travel a little bit more. So this distance traveled is bigger because its velocity is even bigger. And then this one's going to travel even more. And then the next one's traveling even more. It'll be down off of the screen. Okay, so we have one-dimensional motion here. We have one-dimensional motion there. But what happens when both of those happen? What happens when they're happening at the same time? When it rolls off the edge? Well, they do happen at the exact same time. So it's going to move from here to here, but it's also going to move from here to here. It's going to be a combination of the two. It'll end up right there. And this one, at the second instant of time, it's going to be right there. And this one, it's going to be right there. That ball is going to move both in the x and in the y, and it's going to have a motion that follows what we call a parabolic path. When the only force acting on this is gravity, it's not going to slow down or speed up going this way, because gravity only acts up and down. It doesn't affect its side-to-side motion. We're going to be looking at motion like this in two different ways. We're going to be doing a virtual video analysis lab, and I really wish you'd be here for it because it's super fun, but it's not as much fun as the hands-on version we're going to do after that, where we're going to actually be launching cannonballs. They're not very big cannonballs, but still, cannonballs nonetheless. It's one of my favorite labs that we do. We're going to do it with you. We're going to get you the data, and you're going to do the analysis.
So, Dr. Johnson, you said the word parabola.
I did.
Isn't the formula for parabola like y to the second power and x to the first power?
Something like that?
Okay, yeah, I said the other way. Yeah,
Okay.
but yeah, okay. So that means that like with the horizontal, it's just to the first power,
Yeah.
but the vertical's to the second power.
Yeah.
Cool.
So the math is fun. It gets a little bit more interesting than just a straight, plain, boring straight line.
All right, cool.
Any other questions? Shall we get going?
Yes.
Let's do it. Okay, for the first part of this lab, we're going to be doing a video analysis. So we're opening up Logger Pro. You can see Logger Pro is now open on the screen. And we have inserted a video. Now you're going to need to know how to do this at some point, so I'm going to show you. If you want to open a Logger Pro file, you can do File, Open, and find the file you want to open. But that's going to open a Logger Pro file, not a video file. If I already have Logger Pro open, I want to insert a video into my Logger Pro file. I go over to Insert. So let's say I have a video file that I want to put into a Logger Pro and do an analysis of. I insert and choose Movie, and then you just find the movie that you want to insert. If you try to insert movie and open a file, a Logger Pro file, it won't work. So you have to make sure you do the right thing for what you want to do. If the lab tells you to open a Logger Pro file, then you're going to go File, Open. If it tells you to insert a movie, then you go Insert and choose Movie. Fair enough? Does that make sense, Professor Ashcraft?
I think so.
Okay, good. Now we've already done that. It's already open. It's right here. Sometimes when you're in here and trying to do these things, they can be more difficult to find, but that's something that we can help you with. Okay, so in order to be as accurate as I can be, I'm going to make the video window as big as I can. And oh no, there are no buttons here. Where'd the buttons go? I don't know what to do. Well, that's a bold-faced lie. I know exactly what to do. I click on this button right here, and that's going to show me the other buttons that I have at my disposal. All right, so in this video, I clicked on the wrong spot there. So in this video, we have a person just throwing a basketball up in the air, and it bounces a couple times on the ground. Okay, awesome. I need to do a couple things. I need to set my scale. Professor Ashcraft showed you how to do this, I think, but if he didn't, I'm going to show you how to do it as well. As we've said before, if you hover over these, it tells you what they are. So easy enough. I'm going to set my scale. I'm going to click on one end of this measuring tape on the ground and drag it out to the other end. And that is going to be a 2-meter scale. So 2 meters is equal to this length right there, if you can see what I'm pointing at. The mouse is a little sticky right now. It's not listening to me quite well. Okay, so now we want to track the motion of this basketball through space as it goes through its trajectory. I'm going to add points. I can also set my origin. I forgot to do that. That's going to be down here somewhere. Oh, that's show origin. Set origin, right here. I'm going to set the origin at the initial point of the basketball. It doesn't have to be that. It could be anywhere. I could have the origin on the floor. It's just going to change. It's going to shift where the data is at depending on where I put the origin. So we're going to keep it there. Next, I need to track the motion of the basketball, which means I'm going to have to put a point in the center of mass, or the middle of the basketball, for each frame of the video. I'm going to click on the Add Point button. I'm going to move my cursor directly to the middle of the basketball, and I'm going to click. As soon as I click, it advances it 1 frame, and I can click again. And I'm just going to keep clicking. I'm probably going to fast forward this in the video. Now we have all our data points. I'm going to go to Page. You can see I'm clicking on Page and Auto Arrange. It's going to organize my data, and we've got a couple of graphs. So this is really interesting. Check this blue line out. The blue line is showing my Y position with respect to time. Notice that it goes up and then it comes back down, but how is the position becoming negative? Professor Ashcraft, do you have any idea how that works?
Well, yeah, I mean, that's your Y, isn't it?
Yeah, that's my Y.
And you set your origin like at the guy's head.
Yeah, actually just above his head.
So the floor that means the floor is gonna be below his head, so it's negative.
So it's below the origin, therefore it's negative.
Yeah.
X, on the other hand, is never negative because it's only moving to the right, which we have declared to be the positive direction. Interestingly, it's got a certain slope here, and then suddenly the slope changes. Any thoughts on why that slope is changing?
Well, something, the speed, the velocity's changing.
Yeah, something
So-
happens there. Where does that happen? About 1.5 seconds in. So
Oh, when it hits the floor.
right there. Check that out. So it hits the floor and its x velocity changes. Until it hits the floor, there's nothing to slow it down in the x direction. It just keeps moving at the same velocity in the x direction. Constant velocity in the x direction
Huh.
until it hits the ground, until there's some outside force. In the y direction, the velocity is never constant. It's always changing. It's curved because there is a force acting on it, which is causing it to change its velocity. Curved lines in a position time graph indicate some sort of change in velocity because the slope's changing. So what is the thing that's causing it to change in the up and down direction?
Gravity.
Gravity, because it's a projectile, and I told you projectile is the only thing that we're considering acting on it is the gravitational force. So there's a gravitational force acting on it.
So as long as it's in the air, it's a projectile. But once something touches it, like the guy's hand or the floor, then all bets are off, it's no longer a projectile.
Then there's other forces, external forces acting on it, so it won't follow projectile motion.
So when it bounces back up in the air, it's a projectile again.
Yep.
Okay.
So if I click on the y-axis here, I can decide what it's going to show. And if I show the x velocity, actually, I think you'll know what it's going to look like, you being the audience, because we have two straight lines here in the position graph. So the velocity graph should be two constant velocities. So I click on the velocity, and we talked about how sometimes the data is a little noisy. This part is where it's in his hand, and it's accelerating because he's causing it to accelerate. He's pushing the ball. But when it leaves his hand, the velocity is pretty much a flat line. There's a little bit of noise there, but pretty much a flat line. Then there's a sloping area when it hits the ground, and then again, pretty much a straight line right here.
So if you did statistics on, that clump of points up top, would the mean be pretty close to the slope of the position versus time graph for that?
It should be. So I can do statistics. The mean is 3.1. Let's go back to our x. Select this, and we can do a linear fit. Slope is 3.1,
Whoa, okay.
almost exactly.
Yeah.
Pretty cool. I love it when math works for me. Now, how about the y graph? If I make a y velocity graph, so this is the y position graph, what's the y velocity graph going to look like, do you think? So the slope is always changing. We talked about this, right? We talked about this with the match the graph. We talked about it with in week 1 even.
You used the word parabola in your pre-lab.
Yeah, so we have a somewhat parabolic shape right here, actually all the way down into here. We have an object that's going up, slowing down. Right here it's a flat line. The slope of the line there is going to be 0. And then the slope, which was positive over here, becomes negative over here. This should sound familiar. It's something we have talked about before. The object's going up, but it's slowing down. It's got a positive velocity initially, but a negative acceleration. So if I flip over to the y velocity graph, look at that.
Whoa.
That is pretty cool. So this is a velocity that is going from positive to negative. It's going from big positive to small positive to 0 to small negative to big negative as it's speeding up on its way down. And Professor Ashcraft, what's the slope of this graph going to be again? Do you remember what that tells us?
The acceleration?
That's going to be the acceleration. You got it. And, which you probably have learned in your lecture, we would expect the acceleration to be somewhere around 9.
Minus 10?
Yep. 9.8, 9.9, somewhere in that range, and we have almost exactly -10. Anything to add, Professor Ashcraft?
Well, it becomes airborne again, you know, on that bounce. What's the slope over there?
Let's find out. If you're wondering what I'm doing, sorry, I should talk through this because you got to learn how to use the software. I am highlighting the area of data I want to analyze. I'm choosing Analyze, and I'm going to Linear Fit because I'm trying to match a straight line onto the data.
Minus 10.3.
And that's, I believe, within a reasonable amount of error.
One last thing, we did a linear fit for the bounce and the acceleration for the bounce.
Okay, so great. We've done our initial analysis. Now it's up to you guys. I'm going to provide the data for you in some files on Blackboard, and you're going to answer the questions on the rest of this lab. And then we'll move on to the hands-on version. So there, Professor Ashcraft and I are going to be firing some candidates, so it's going to be a lot of fun.